Lastly, problem number 2 from the 2017 AP exam. Well, isn't this just beautiful? Let's get the speed of the block right before it collides with the spring. Is this a smooth floor? Let's find out. Smooth transition. There is negligible friction. Negligible friction, negligible friction. Very nice. All right, so let's get that speed. mgh equals 1/2 mv squared. And we get 2gh under a square root equals v. Yes. Now, is the speed halfway down the inclined plane greater than, less than, or equal to 1/2 the speed down the bottom of the inclined plane? It's very easy to do this. V equals the square root, so v 1/2 down is going to be square root of 2g h over 2, which is going to be the square root of gh, versus v down the total bottom is going to be square root of 2gh. So the issue here is 1 over 2 versus 1 over square root of 2 when I take these ratios, because is it 1/2 the speed, or is it, when I take the ratio of v 1/2 to v at the bottom, that's 1 over square root of 2, which actually is going to be greater than, since 1 over 2 is bigger than 1 over the square root of 2. So that's my reasoning. Basically, I just found v 1/2 and v at the bottom, and took the ratio, and I realized I got 1 over square root of 2, which is, less than, let me say that one more time. 1/2 is less than 1 over square root of 2, which is the ratio of v 1/2 to v. So what that means is the speed half the way down is bigger than half the speed at the bottom of the inclined plane. Now it says derive an expression for the maximum compression of the spring. Do we have K? So I'll keep it simple. I'll actually convert the gravitational energy into 1/2 kx squared. So I'm just going to say 2 mgh over k. Ooh, that's hard to read. Let me make that simpler. We will say that here mgh equals 1/2 mv squared, which gets converted to 1/2 kx squared. So our compression is going to be 2 mgh over k, all under a square root. Excellent. Now the block is released again, and we're going to have this resistive force. So we want to set up but not solve the differential equation as a function of distance. So it's going to be simple. We're going to have this force that slows it down, negative beta v squared, equals m dv dt. And what we're going to note is that v of 0 equals v naught. So when we solve this differential equation, this looks gross, but it actually turns out it's a little bit easier than you think, and here's why. So we have negative bv squared equals m dv dt. Y'all, we've got one trick, and here's the trick. Separation of variables. So negative beta dt equals, so negative beta over m dt equals dv over v squared. I'm going to integrate this. So on this left side, we're going to end up getting negative beta, negative bt over m equals, and then here we're going to get negative 1 over v, and we're integrating that from v naught to whatever v we end up at. So when we actually work this out, we're going to end up getting negative beta t over m equals 1 over v naught minus 1 over v, and when we simplify, we're going to end up getting 1 over v equals 1 over v naught plus beta t over m. Okay. So this side we're just integrating from 0 to v naught, and this we're integrating from 0 to t. Or you can do it with initial conditions the way we did before. So that is part D. Now for part E, it's important that we actually take a look at what's going on in terms of the forces. So just kind of keeping this simple, let's just note here that in this problem, we are going to end up having here that the force is negative bv squared. And of course, we're always going to have some kind of a terminal velocity in a situation like this. In this case, what's actually going to happen is that our terminal velocity is going to be 0 because it will stop. So we have a v naught here, and then our velocity just kind of decays in time and approaches 0. What that tells us about our acceleration is, since it's a negative acceleration that's going against the speed, it will eventually level off. And then what this also tells us for our position is that we start off at 0, and then we kind of approach sort of an asymptotic limit. I might maybe draw the acceleration a little bit more like this, sort of approaching kind of a limit like that and leveling off near 0. So that is how I would do my graphs.